In this video, we'd study the second technique of integration, and this is known as trigonometric substitution, or trig sub for short. So this method involves converting integrals that contain one of these three forms, either the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared. For the first, this is essentially a sine substitution. The second one is a tangent substitution. The third is a secant substitution. And in this video, we're going to look at each of these three types individually. First, we look at integrals that involve square root of a squared minus x squared. All right, so first, notice that the domain of the square root of a squared minus x squared, negative a, less than or equal to x, less than or equal to a, which would mean that we take negative 1 less than or equal to x over a, which is less than or equal to 1. Notice also that the range of sine theta over negative pi over 2 to pi over 2 is negative 1 to 1. What this means is there exists a unique angle theta in negative pi over 2 to pi over 2 such that sine of theta is equal to x over a, which means x is a times the sine of theta. So we try to take this as our substitution. And now let's see what happens. So we have square root of a squared minus x squared, but we just said x is a sine theta. All right, so what does that equal? We get square root of a squared minus a squared sine squared. We can factor out an a squared, be left with 1 minus sine squared. But 1 minus sine squared is cosine squared. So we have absolute value of a times the cosine of theta. Well, we assume that a is positive, right? That's a safe assumption. So a is greater than 0. And notice that cosine of theta is greater than 0 over the interval negative pi over 2 to pi over 2. Thus, we have the following substitution. X is a sine of theta. Dx would be a times cosine of theta d theta. And our actual square root, a squared minus x squared, becomes a times cosine of theta. So this is the substitution we make if our integrand involves the form square root of a squared minus x squared. Next, let's look at the case where the integrand has the form square root a squared plus x squared, And of course, notice we could also have the square root of x squared plus a squared. Same thing, right? Because remember, addition itself is commutative. So notice, again, the domain of square root of a squared plus x squared in this case is all real numbers, minus infinity to infinity. Also notice range of tangent of theta over negative pi over 2 to positive pi over 2 is also all real numbers. What this means is that we have a unique angle theta in the domain negative pi over 2 to pi over 2 such that tangent of theta is equal to x over a, or x is equal to a times tangent of theta. So we try this substitution, and let's see what we get. Take the square root of a squared plus x squared. We just said x is a tangent of theta. And factor out, or I'm sorry, not factor out yet. This becomes a squared plus a squared tangent square root of theta. We can factor out that a squared. But 1 plus tangent square root of theta is secant square root of theta. So this equals the absolute value of a times secant of theta. Well, again, a is greater than 0. Also notice that secant of theta would also be greater than 0 over negative pi over 2 to pi over 2. I should say greater than or equal to 0. So we can have the following substitutions. X is a times tangent of theta. Dx would be a times tangent squared of theta d theta. And then the square root of a squared plus x squared is a times the secant of theta. Finally, let's consider our last form, that is an integrand that contains square root of x squared minus a squared. Well, notice here the domain of the square root of x squared minus a squared would be everything except, would be everything except what's between negative a and positive a. Range. If we take a look at the range of secant of theta, this is 0 to pi over 2 unioned with pi over 2 to pi. Oh, I'm sorry, over this domain is also negative infinity to negative 1 unioned with positive 1 to infinity. All right? What this means, right, is we have a unique angle theta in 0 to pi over 2 unioned with pi over 2 to pi, such that secant of theta is equal to x over a, which means x is a times secant of theta. And to see this, I did forget. Up here, this means that x is less than negative a, or x is greater than a, which means that x over a is less than -1, or x over a is greater than +1, right? So that's why we can conclude this down here. If we now look at the square root of x squared minus a squared, x is a secant theta. Right, expand that out. We get a squared secant squared theta minus a squared, square root of all that. Factor out that a squared. And secant squared theta minus 1 is tangent squared. And so we get the absolute value of a times tangent of theta. Now, again, a is greater than 0. We have tangent of theta is greater than or equal to 0. Over 0 to pi over 2. And it is less than 0, less than or equal to 0, over pi over 2 to pi. So we can make the following substitution. X is a times secant of theta. Dx would be a times secant theta tangent theta d theta. And now we have two possibilities for the square root of x squared minus a squared. That'll be a times tangent of theta for x larger than a. Or it could possibly be negative a tangent of theta for x less than negative a. So what I'm going to do is write this actually piecewise. I think that'll be simpler. And so negative a tangent of theta when x is less than negative a. Now, by convention, if we're just simply dealing with an antiderivative, that is an indefinite integral, we will take the positive a tangent of theta instead. Let's now look at several examples, starting with the antiderivative of the square root of 9 minus x squared. Right? Now we look at this, and we go, okay, well, this fits the first form, so let's try the substitution. X equals 3 sine of theta, which would make dx 3 cosine of theta d theta, and the square root of 9 minus x squared becomes 3 cosine theta. All right, so what this all becomes now is we get the antiderivative of 3 cosine theta times 3 cosine theta d theta, which is the antiderivative of 9 cosine squared theta d theta. Now, let's use the identity. Cosine squared of theta is 1/2, 1 plus cosine 2 theta. We'll get 9/2 antiderivative of 1 plus cosine 2 theta d theta. We get 9/2 times the quantity of theta plus 1/2 sine of 2 theta. Obviously plus a constant. Right? And now use the identity for sine of 2 theta. We get 9/2 theta, let's say, plus 9/2 sine of theta cosine of theta plus our constant. Now what we need to do is convert this back into x's. Right? Well, first let's look at theta. Well, theta, we can use sine of theta equals x over 3, right? So theta itself, let's say, is the inverse sine of x over 3 plus 9/2. Now, sine of theta we know is x over 3. Cosine of theta from above, square root 9 minus x squared over 3. Simplifying all this, we're left with 9/2 inverse sine of x over 3 plus x square root 9 minus x squared all over 2 plus a constant. Let's now go ahead and look at the antiderivative. Square root of 4 minus x squared over x dx. Again, this looks like it's going to be a sine substitution, so let's try x equals 2 sine of theta. Dx equals 2 cosine of theta d theta. And the square root of 4 minus x squared will be 2 cosine of theta. What we get is the antiderivative is now this antiderivative. 2 cosine theta over 2 sine theta times 2 cosine of theta d theta. Simplifying that, we'll get 2 times the antiderivative, cosine squared theta over sine theta. Well, let's go ahead and rewrite that. Right, we have cosine over sine, which is cotangent. Then we have 1 over sine, which is cosecant. So we have 2 times the antiderivative of cotangent of theta times cosecant of theta. Well, that's a problem. Right, what is that antiderivative? It's negative cotangent squared, isn't it? Oh, I'm sorry, I did that wrong. No, this would have been cotangent times cosine. I'm sorry. Right? Which is not helpful. So instead, let's rewrite it this way. Right? 1 minus sine squared theta all over sine theta. This then becomes 2 times the antiderivative of cosecant theta minus sine of theta d theta. Right? Antiderivative cosecant theta, negative cosecant cotangent. I'm sorry, natural log of the absolute value, cosecant minus cotangent. Right? Antiderivative of sine is negative cosine, so we get plus cosine of theta. And then plus a constant. What we have to do is write this now in terms of x, right? Well, we know how to write cosine of theta. Problem's going to be this cosecant and this cotangent. Well, let's do this. Let that represent our angle theta. Well, we know that sine of theta is x over 2. Right? So opposite of the angle would be x. The hypotenuse would be length 2. Then this would be the square root of 4 minus x squared. Using that right triangle, cosecant of theta, right, is 1 over sine. So we get 2 over x minus cotangent, right, would be 1 over tangent. So we'll get the square root of 4 minus x squared over x. And of course, obviously, we knew what cosine was. Square root of 4 minus x squared over 2. Now it's just a matter of trying to simplify this. So let's go 2 times the natural log. Absolute value. 2 minus the square root of 4 minus x squared all over x plus the square root of 4 minus x squared plus our constant. Well, let's now look at antiderivative of x cubed times the square root of 1 minus x squared. Now, you see that square root of 1 minus x squared and would probably immediately think of doing a sign substitution. Well, why don't we try writing it this way instead? Antiderivative of x squared times the square root of 1 minus x squared times x dx. Now let's use a u substitution. Let u be 1 minus x squared. This would mean that du is negative 2x dx, and we can write x squared as 1 minus u. Right, well, look at that. What we can now do is write the integral this way. Antiderivative of 1 minus u times u to the 1/2 du, and multiply the whole thing by negative 1/2. All right, so we have negative 1/2 times the antiderivative of u to the 1/2 minus u to the 3/2 du. All right, that is 2/3 u to the 3/2 minus 2/5 u to the 5/2 plus a constant. Right? Now just replace our u's, and we'll get negative 1 minus x squared to the 3/2 over 3 plus 1 minus x squared to the 5/2 over 5 plus a constant. Right, so this one, you could have used trig sub and you get to the same answer. But trig sub was not necessary. So this just goes to show you that there are certain antiderivatives where there is more than one technique to evaluate it. Now, let's take a look at antiderivative dx over the square root of 1 plus x squared. Right? Well, this is a tangent. So let x be tangent theta. Dx is secant squared of theta d theta. And the square root of 1 plus x squared would become secant theta. So our antiderivative becomes the antiderivative secant squared theta d theta over secant theta. Which becomes simply the antiderivative of secant theta d theta. So that antiderivative is the log of the absolute value of secant theta plus tangent theta, and then plus our constant. Right? Well, we know what secant theta is. Square root of 1 plus x squared. We know what tangent theta is. It's x. So here is our antiderivative. Let's now look at the integral from 3 to 5, square root of x squared minus 9 dx. All right. Well, this is going to be x equals 3 secant of theta. Dx is 3 secant theta tangent theta d theta. Now for the square root of x squared minus 9. A is 3. Our x goes from 3 to 5. Right, this means that our x is greater than or equal to 3. So we take the positive. Right, we take 3 tangent of theta. However, we're doing a change of variable. So what we also want to do is change the bounds. Look at the lower bound first. Lower bound is x equals 3. Let's do this in green instead. This would mean that 3 is equal to 3 secant of theta, which means secant of theta itself is 1, which leads to theta being the inverse secant of 1, which is 0. Now, if x is equal to 5, this means that 5 is now 3 secant of theta, which means secant theta is 5 over 3. And so theta would be inverse secant of 5 over 3. What we now get is the integral from 3 to 5 of the square root x squared minus 9 is the integral from 0 to the inverse secant of 5/3 of 3 tangent theta d theta. I'm sorry. Times 3 secant theta tangent theta d theta. Right? This is the integral from 0 to the inverse secant of 5/3 of 9 tangent squared theta times secant theta d theta. So we have integral from 0 to the inverse secant of 5/3. Rewrite tangent squared as 1 plus secant squared. Now distribute that secant squared through. And I think at this point I'm also going to factor out that 9. So let's do 9 times the integral from 0 to inverse secant of 5/3 of secant theta plus secant cubed of theta d theta. I'm sorry, tangent squared is not 1 plus secant squared. It is secant squared minus 1. So the only change that's going to be made is we get secant cubed minus secant. We can use the secant reduction formula. So secant cubed and antiderivative is going to be 1/2 tangent times secant plus 1/2 the antiderivative of secant theta. If we plug that in, what we get is 9 times the integral secant inverse secant 5/3 secant cubed minus secant becomes 9/2 tangent times secant evaluated theta equals 0 to the inverse secant of 5/3. Right, we're going to have minus 9/2 secant theta plus 9/2 secant theta minus 9. This should leave us, I'm trying to follow along with what I did. It should leave us with minus 9/2 the antiderivative, 0 to inverse secant of 5/3 secant theta d theta. Yes, that's correct. Right, they both have 9/2, so let's go ahead and factor out that 9/2. What are we left with? We're left with tangent theta secant theta minus the natural log of the absolute value of secant theta plus tangent theta evaluated theta equals 0 to inverse secant of 5/3. Right now, let's just go ahead and plug it in. 9/2 times the tangent of the inverse secant of 5/3 times secant of the inverse secant, which is just 5/3. Then we get minus natural log, absolute value of 5/3 plus tangent of the inverse secant of 5/3. Let's say minus 9/2 tangent of 0 times secant of 0. Tangent of 0 is 0, so that piece goes away. Negative log secant of 0 is 0. Tangent of 0 is 1. Well, this piece, right, log of 1 is 0, so that entire piece goes to 0. So we're left with just whatever this is going to evaluate out to. To determine what tangent of inverse secant of 5/3 is, again, let's go ahead and make a right triangle. This is our inverse secant of 5/3 angle. Right, that would make the hypotenuse 5, the adjacent side 3. That would make the opposite side 4. Right, so now if we take the tangent of that angle, it's just 4/3. So this becomes 9/2 times the quantity, 4/3 times 5/3, which is 20 over 9, minus natural log of the absolute value of 5/3 plus 4/3. So we get 9/2 the quantity, 20 over 9 minus natural log of 3. Distribute that 9/2 through. 10 minus 9/2 log of 3. Okay. Let's now look at the antiderivative of dx over 4 minus x squared raised to the 3/2 power. Well, we see a 4 minus x squared, so let's try x equals 2 sine of theta. Dx would then be 2 cosine of theta. Square root of 4 minus x squared would be 2 cosine of theta, and I forgot my d theta. Right, so our antiderivative now becomes antiderivative 2 cosine theta d theta over, well, wouldn't this be 2 cosine of theta cubed? Right, 3/2 is square root cubed. We can factor out a 1/4. We're left with cosine over cosine cubed, so this just becomes d theta over cosine squared. This is a quarter antiderivative of secant squared theta d theta. Antiderivative of secant squared is tangent. That's our angle theta, right? We had sine of theta is x over 2. So there we go. Tangent theta would then be x over square root of 4 minus x squared. Just writing this simpler, we get x over 4 square root of 4 minus x squared plus a constant as our antiderivative. Finally, let's consider the antiderivative of dx over x squared plus 2x plus 3 raised to the 3/2 power. Well, this does not fit the form a squared plus x squared, a squared minus x squared, or x squared minus a squared. But let's take a look at x squared plus 2x plus 3, and let's do a common technique known as completing the square. So we get x squared plus 2x. Half of 2 is 1. Squared is still 1. Right, well, now we just have to add 1 to 3. I'm sorry. We're subtracting 1 from 3. Right, because we can write 3 as 2 plus 1. So there we go. Now notice what we get. We get x plus 1 squared plus 2. So our antiderivative now has this form. Dx over the quantity of x plus 1 squared plus 2 raised to the 3/2 power. Let's now do a u sub. U is x plus 1. clearly du is just dx. Using that substitution, we now have this form. Antiderivative of du over u squared plus 2 to the 3 halves. Now this fits the tangent form. So let's say u is the square root of 2 times tangent of theta. Du would be the square root of 2 times secant squared of theta d theta. And the square root of u squared plus 2 would wind up being square root of 2 secant theta. What we've now done is we've taken our antiderivative and we've written it in this form. Square root of 2 secant squared theta d theta over square root of 2 secant of theta cubed. If we simplify this, we can factor out a 1/2. What we're left with is then d theta over secant of theta. Well, this is then just 1/2 antiderivative of cosine of theta d theta. That gives us 1/2 sine theta plus a constant. Right? We knew that tangent of theta is x over the square root of 2. I'm sorry, not x, it's u. So sine of theta would be u over the square root of u squared plus 2. Now replace u. Which was x plus 1. Right, so we get x plus 1 over 2 times the square root x squared plus 2x plus 3 plus a constant. Right? The square root of x squared plus 2x plus 3 comes from the fact, remember, that u squared plus 2 came from x squared plus 2x plus 3, the completing the square part. So there is our antiderivative.